about what powers the sun and how it works. And this is an excerpt from the chapter called Shelter from the Storm, which we started last night. The mathematical theory of beta decay, that's when atoms release an electron during their subatomic decay process. Okay. The mathematical theory of beta decay was developed by Enrico Fermi in 1934 in a paper that was rejected by the journal Nature because it contained, quote, it contained speculations too remote from reality to be of interest to the reader, end quote. Neutrinos from a nuclear reactor were first detected by Clyde Cowan and Fred Rines in 1956. So it turns out they were a real thing. We have already seen that based on the work of Hans Bethe and his colleagues. We believe that 4 hydrogen nuclei are burned into a single helium nucleus, plus 2 positive electrons and 2 neutrinos, plus energy. This means that from the very core of the sun, from its energy generation regions, far beyond all sight, from which radiant energy takes 100,000 years to emerge, there are particles that escape as if the surrounding sun were not there at all. If we could detect these solar neutrinos, we would be able to look into the heart of the sun and measure what the conditions were like there at the moment. We can calculate how many neutrinos are arriving at Earth direct from the sun's core. The answer is about 100 million of them per square meter per second. Billions are passing through your body every second, doing you no harm whatever. In 1964, an experiment was proposed to try to detect neutrinos. It was suggested that a huge tank containing 100,000 gallons of cleaning fluid per chloroethylene, which is mostly composed of chlorine, could detect the neutrinos from the sun. When neutrinos collide with a chlorine nucleus, they produce a radioactive isotope of argon. This happens very rarely, but if there is a large flux of them through the tank, a few of them might collide occasionally. All you had to do was examine the tank every once in a while and measure the argon concentration, and you could estimate the neutrino flux passing through the tank from the sun. Just a few atoms would be produced per week in a huge Olympic-sized swimming pool of cleaning fluid. The tank was set up 5,000 feet underground in the Homestake gold mine in South Dakota. Underneath all that rock, the tank would be shielded from cosmic rays that could cause confusion. The solid rock was, of course, irrelevant to the neutrinos. In 1968, it was announced that fewer neutrinos than predicted had been detected coming from the sun. At first, scientists thought there was something wrong with the tricky experiment. But the discrepancy persisted. There really were far fewer neutrinos coming out of the sun than theory predicted. So was the theory of energy production inside the sun wrong, or did something happen to the neutrinos after they were created in the sun? It seemed inconceivable that the theory was wrong. Perhaps the sun's central temperature was slightly lower than we thought, which would affect the emerging neutrino flux. But even that would cause problems for our understanding of the stability and lifetime of stars. Perhaps the most imaginative proposal was made by Stephen Hawking, who suggested that the central region of the sun might contain a small black hole, and that this could be the reason that the number of neutrinos observed was less than the predicted number. But as early as 1969, 2 scientists working in Russia proposed that the discrepancy between standard theory and the first solar neutrino experiment could be due to the behavior of the neutrinos themselves. Gribov and Pontecorvo suggested that neutrinos suffer from a multiple personality disorder, and that they oscillate back and forth between different states or types. According to these scientists, neutrinos of different types are produced in the sun. As they travel to the Earth from the sun, the neutrinos oscillate between easier to detect neutrino state and the more difficult to detect neutrino state. The chlorine experiment only detects neutrinos in the easier to observe state, so the measured flux was low. Over the next few decades, physicists built a series of underground detectors designed to detect neutrinos. This time, they did not use cleaning fluid but water. They lined the tanks with light detectors that could pick out any flashes of light from the water. Occasionally, a neutrino would cause a flash in the tank, which would be detected. In 1986, Japanese physicists used such a huge tank of water designed to measure the stability of matter. The experiment, called Kamiokanda, in the Japanese Alps, detected solar neutrinos and confirmed that the neutrino rate was less than predicted by standard physics and standard models of the sun. So far, neutrinos produced in the center of the sun have been detected in 5 experiments. But neutrinos also produced by the collisions of cosmic ray particles with other particles in, neutrinos are also produced by collisions of cosmic ray particles with other particles in the Earth's atmosphere. In 1998, the Super Kamiokande team of experimentalists announced that they had observed oscillations between atmospheric neutrinos. So it now seems that the mystery that once threatened to undermine our understanding of the sun has gone away. As for the scientist who had the audacity to fill an underground tank with chlorine cleaning fluid, Raymond Davis Jr. won the 2002 Nobel Prize for Physics. Solar radiation. Neutrinos pose no problems for astronauts, but the sun produces many other forms of radiation that do. Imagine it is 1972 and the last planned manned mission to the moon, Apollo 17, is canceled after the death of the crew of Apollo 16 when returning to the Earth after their moon landing. The United States and the world are stunned by the loss of three brave astronauts who succumbed to radiation in space and became too ill to control their spacecraft during its return. It could have happened. From time to time, the sun unleashes monster flares that could put astronauts traveling to the moon and beyond in great jeopardy. The plan for the Apollo lunar missions, which placed 12 people in the on the lunar surface between 1969 and 1972, called for low-altitude Earth orbits and then a rapid transit to the moon. While in low Earth orbit, the Earth's magnetic field shelters astronauts from harmful solar radiation. The worry on all lunar missions was a sudden explosion on the sun and the release of vast amounts of radiation while the astronauts were beyond the Earth's protective custody. It was to keep a watch for such unexpected events that before and during the Apollo missions, the sun was maintained under close scrutiny. The Solar Particle Alert Network monitored solar flares. A prognosis for the expected radiation dose the astronauts might experience was prepared and continually updated by radiation environment specialists sitting at a console in the Apollo Mission Control Center in Houston. The dose estimates were given to the medical officer who advised the flight director of the radiation effects to be expected. On board the Apollo spacecraft, there were radiation monitors, and each astronaut carried a personal dosimeter, which measured his accumulated skin dose. A portable dose rate meter was also carried in the lunar module and onto the lunar surface. In August 1972, preparations were well underway for the Apollo 17 mission to the Taurus-Littrow region of the moon in December. It was to be the final moon landing, as Apollos 18 through 20 had been canceled. The previous Apollo mission, in April to the plains of Descartes, had been a resounding success. But that summer month, something happened that had literally frightened mission controllers and made them realize if they needed any reminding how dangerous was a flight to the moon. The August 1972 solar flare was a monster that above the Earth's protective magnetic sheath delivered unshielded radiation doses of 20,000 rem. It is thought that flares with such particle fluxes occur only about 1 day per decade, but the implications of any crew being caught out in such an event are terrifying. The RIM is a standard measurement of radiation exposure. On a normal Apollo mission to the moon, the worst the astronauts would expect was about 1 RIM, which comes from transit through the Van Allen radiation belts that surround the Earth. The U.S. Space Agency specifies a 30-day exposure limit of 25 RIM, and the terrestrial occupational limit for radiation workers is 5 RIM in a year. The average lethal dose is 450 RIM, which means that any astronaut in space or on the moon's surface at the time of the August 1972 solar flare would have suffered a lethal exposure if they could not find protection. But what would have happened if 2 astronauts had been working on the lunar surface and a third had been in orbit around the moon on that August day and had suffered an exposure of about almost 20,000 REM? Between 25 and 100 REM, there's an increased probability of leukemia during the unfortunate person's lifetime and damage to their germ cells, which could mean they could pass on genetic defects to their offspring. Between 100 and 250 REM, nausea and vomiting occur within hours, and there's a high incidence of leukemia in a shortened life. Untreated, it can lead to death. Between 250 and 750 REM, there is nausea and vomiting after about an hour, along with acute shock. Death is likely within a month if untreated. There will be cancers, cataracts, and significant life shortening and sterility. Between 750 and 2000 REM, there is nausea and vomiting within an hour, unconsciousness, then a temporary return to consciousness, but death within a week. Above 2000 REM, the crew would be unconscious in minutes, with a brief recovery, then death. In the one recorded instance of 10,000 REM exposure, death occurred within 38 hours, incapacitance much sooner. The fact is that if we were to explore the moon and go on to Mars, then someday astronauts will have to deal with and survive a big solar flare. Flares large enough to require shielding occur perhaps several times a year. There have been many studies in relation to the moon, and all follow the principle of placing as much mass as possible between the astronaut and the sun. Perhaps we must position the first manned outposts on the moon near the lunar poles, where there are regions that sunlight can never get to, and where a shelter on the poleward side of a crater wall or in a permanently dark polar crater would provide protection. If we build bases elsewhere on the moon, we had best bury them in as much lunar dirt as we can manage. Long traverse pressurized lunar rovers present special problems since the maximum solar flare warning is currently just 3 hours. So the time needed for astronauts to reach shelter would be likely to exceed the onset of the flare. Designs have called for such vehicles to carry an inflatable shield that can be buried under lunar dirt. Outside the Earth's magnetic shield, the magnetosphere, an interplanetary astronaut caught by such a flare would also need some sort of special protection. The Apollo astronauts reported seeing occasional flashes in their eyes during the moon missions, and close examination of their helmets revealed microscopic holes where high-velocity particles, hydrogen and helium nuclei, had tunneled through the spacecraft, through their helmet and through their heads. Some of these particles were cosmic, coming from outside our solar system, but many others are thought to have been solar in origin. The traverse to Mars will probably take the best part of a year. Even if we use new generation nuclear propulsion yet to be designed and tested, the flight time to Mars would be reduced to perhaps 4 months. This means that there would have to be some form of storm shelter in the depths of the spacecraft, surrounded by as much hardware as possible. Perhaps the shelter would be at the end of the spacecraft with the vehicle turning to face the sun, placing the maximum amount of material between the sun and the astronauts. One thing is for sure, wherever astronauts roam in our solar system, they will sometimes have to hide from the sun. And that's where I'll stop. That's the end of chapter 25. Our next chapter will be called The Rescue of Solar Max. I'm not sure what that is, but we'll find out. I love you, and sleep tight, and don't let the chappies bite. And I'm blowing you some kisses. Mwah, 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 mwah. Good night. Sweet dreams.